So now that we've got it straight exactly what we have to do to prove a logical or a set equivalence using logical operators and logical equivalences, let's do it for one of DeMorgan's laws. So this one is actually exercise E from John Hammond's notes. It's the exact same as exercise E. And again, if you haven't seen the last video yet, what we need to do here is we need to actually show two things, right? We need to show that the left-hand side, A union B complement, is a subset of the right-hand side, A complement intersected with B complement, and we have to also show that the other direction is true, right? That A complement intersect B complement is a subset of A union B complement. All right, and in my lecture notes in the video in the slide, this is misleading, okay? But we have to do both of these. It's not just misleading, it was wrong, so I'm going to fix that. I apologize, but so we have to do both of these. So let's start with the left-hand side. I like to label these by the direction that it's written up here, I guess. So there's one direction. You don't really have to do this if you don't want to, but let's suppose that we have an element x in the complement of the union. Okay, whenever there's a complement, the complement is the negation symbol from logic. If x is in the complement of A union B, that means that x is not in A union B, right? That's what it means to be in the complement. It's not in that set. It's in some universal set, and I talked about this in the slide in the lecture notes, lecture slide video. But it's in the universal set. It's just, to us, we don't really care what the universal set is here, so we're not concerned with it being in the universal set, right? What we are concerned with is that it's not in this set, because if it's in the complement, then it's not in this set. All right? Now, we have to be a little careful with this. So once we have a negation, then we have to be careful with how we represent this symbol, right? So this means that x is not in A union B. A union B is the collection of all elements that are in A or in B, right? Or both. Remember, this is an inclusive or. So in A or in B or in both. But when we negate that, we actually end up with the AND logic symbol, all right? And so this is one of our logical equivalences. So this means that x is not in A and x is not in B, right? Because if it were in either one of them, then it would be in the union, right? So there we go, we've got that. Now we just rewrite this in terms of what the complement again. So if x is not in A, then actually x is in A complement, right? We don't change this because we're not changing the, we're not negating this, right? We're changing the negation from the element symbol here, the containment symbol, to the set itself. So this is still an OR, right? So it's x is in A complement or x is in B complement. And then we can use the set definition here of the disjunction, and that becomes the intersection, right? So I think I said or a minute ago, but this is an and, right? So x is in A complement and x is in B complement. So this becomes the intersection. So x is then in A complement intersected with B complement. All right, and so what do we learn then? We learned that the union, the complement of the union, A union B complement, is contained in, subset of, A complement intersected with B complement. Okay, so we have to now show the other direction, right? And I think I said this in the last video, but it's pretty easy to see that all of these arrows are reversible. You can just reverse this, but let's write it down, okay? So let's actually work it out so that we understand what's happening here. So for the reverse direction, we have to start with our element on the other side, right? So let's let x be an element of A complement intersected with B complement. And then unpack this, right? So if we unpack this, the first thing we want to do is we want to distribute the x kind of and say it like this. So x is in A complement and x is in B complement. All right, so we get the elements in front of each of the terms, and then we can deal with the complements, right? So at this point, we deal with the complements. So that means x is not in A and x is not in B. Okay, that's what it means to be a complement. The complement is just a negation. All right. Same thing here. We want to kind of pull the x not in symbol out. But when we do that, because this is a negation, we have to negate the conjunction and make it a disjunction. All right, this is actually DeMorgan's law for sets, right? So X is then not in. What is it not in? Well, when we pull it out like this, this has to be, it's not in the set A or, so, I mean, I guess the way I'm writing it, I'm skipping a step here, right? Or no, I guess it's right. But when we pull this out, this has to become the union symbol, right? It's not in the union here. All right, so when these all come out, the conjunction becomes the equivalent of the disjunction. That's by DeMorgan's law for logic, right? And it shouldn't be a surprise that DeMorgan's law for logic is playing a big role here, because this is DeMorgan's law for sets, right? Last step is, if X is not an element of this union, then X is an element of the complement of the union, right? And so at this point, we have finished everything. We just need to write it out, right? So this tells us that A complement intersect B complement is a subset of A union B complement of the whole thing. We've got our subset containment going both directions now, right? And by our logic definition of set equality, this means that these two sets are actually equal to each other, right? A union B complement is equal to A complement intersected with B complement. And that's all it takes.